Okay, my name is John Shackleton. I work for Adventium Labs out of Minneapolis, and it occurs to me that I think the title of this talk is a little bit misleading, making migration more secure. If you're watching this and you're hoping to find some new exploits in the migration code of your favorite tool stack, that's not what I'm going to talk about, although that's what it's suggested by the title. I think a better title would be perhaps making migration behave properly in a more secure architecture. But that's a lot to say, so we'll just keep the same title for now. I'll explain what I mean by secure architecture in a minute, but first, let me give you the scenario that I'm working with here. I think the best way is to give an example scenario. So suppose you have, you're a manufacturing company and you have multiple suppliers. These suppliers are competitors of each other, and yet you have separate projects and you're collaborating with them. All the information is kept on your servers, and you want to maintain your cloud environment, but you also want it to be secure as well. And so that is a challenge. Adding other factors on top of that, you might have export control issues. So each of these suppliers then have to maintain some strict isolation between each other, and yet you want that cloud infrastructure in place for all its benefits. And so the challenge then is, how do you maintain those two suppliers perhaps on the same server in the face of different types of cyber attacks? So perhaps one of the suppliers is not playing nice, they go rogue and they attack the server trying to get some information on the other supplier. Can your server environment withstand a cyber attack like that? For example, if they compromise DOM0, can you still provide some guarantees that that rogue supplier has not gained access to the other supplier's information? Some of the techniques to do that have been discussed at length already this morning, and I will review some of those. What I'm going to talk about instead is, with those techniques in place, how does that impact migration? And it turns out that it makes the migration operation very interesting. So with that, let's go over a few terms here before we jump into the details. When we talk about migration, clearly it's important to understand what the underlying storage mechanisms you're using. There's 4 basic types. Not all of these we've addressed in our prototypes, but I'll go through all 4 of them here now. The most common type is the shared disk, where your virtual machine images are stored on a centralized network storage. And in that case, when a migration occurs, the actual image doesn't have to physically go anywhere. All that's passed between server A and server B in this case is the metadata. And the protocol that's used on the shared disk is like your iSCSI or NFS or fiber channel. That's the most common, certainly in a cloud environment. Moving on, you can have replicated disks, so that's a situation where you're using underlying hardware technology to provide that replication through the VMs. In that case, it's really not a software solution, it's more of a hardware solution. Remote referencing is kind of an unusual scenario. That's where you're using an underlying network protocol like NBD is the Linux utility, wherein when the migration takes place, the image is not actually passed. It's physically still in the same server originated in, but then the destination server simply points back to the original image. It's a little bit unusual. That one we're not considering, but for completeness, I mention it here. And then finally, we have the so-called shared nothing situation, where there is no networked shared resources all in the storage, and that is you have a local copy of your virtual machine on one server, and you do a full copy onto the destination server. And in that case, there's no sharing involved at all. It has to fully copy that entire image in an iterative way without disruption of the operation of the virtual machine itself. So in our prototypes, and what we've worked with is primarily with the shared nothing or the shared disk environment. And actually, we concentrate mostly on the shared disk because that's the easiest one to work with. Because with a shared disk, migration takes only a few seconds. You're only passing the metadata. Whereas in the case where you're just using the local storage for shared nothing situation, you're copying the entire image. So that can take 5 to 10 minutes, depending on your network connection and how large your image is. So for development purposes, it's much easier to work with shared network storage. So before we continue, let's just review what the basic migration process is. Each tool stack will do it slightly differently. They all have their implementations and their various points of optimization, but in general, it's kind of a solved problem. They all kind of follow the same basic process. You create a mirror between the two servers, and then during that process of creating that mirror, it's iteratively copying the virtual machine image from point A to point B, and so that it does a copy, and then it goes back and sees what's changed while that virtual machine continues to operate and continues to run, and then it iteratively does that until the delta between the changes is so small that the final migration is ready to take place. Pauses the virtual machine, transfers the metadata, which is usually just a few megabytes, resumes the VM on the destination server, removes the mirror, and then releases the footprint from the original server. So this is the basic process. It's called live migration because you can migrate virtual machines between servers without interrupting the operation of the virtual machine. And it's really the operation that separates cloud type virtualization versus something like a client-based virtualization. And it's a process that's been in place for a long time, and like I said, it's mostly considered a solved problem at this point. So, like I said before, I'm not necessarily interested at this point in sort of low-level bugs or exploits that are out there, although I'm sure there are some. Migration is a very complicated operation. But I'm really more interested, our team is really more interested in sort of these high-level attacks, things that more sophisticated threats would incur in order to exfiltrate or disrupt the system. So things like spoofing, for example. Now, for the most part, spoofing is not necessarily a problem with migration. It is something to consider, but most tool stacks will use some kind of authentication and encryption when they implement migration. And so that's not something we've necessarily concentrated on, but it is something to consider. Just for background, spoofing would be a case where you have a server that a server that's not part of the system, and that's not that's a bad actor, effectively. It's maliciously inserted into the system, and it tries to pretend like it's part of the system, or tries to pretend like it's a specific server on the system already, with the intention of trying to acquire a virtual machine in a migration. Thrashing is a sophisticated DOS type attack. So with thrashing, a lot of these cloud type environments, they have automated migration. So in these cases, for load balancing purposes, they'll have algorithms that say, you know, if the load reaches 80% on this server, try to migrate some virtual machines off to another server in order to do some load balancing. Well, one type of attack would be you purposely load up a malicious virtual machine on server A in order to try to disrupt the system by having it spend so much time in doing the migration process instead of doing its normal processing. So it's sort of a sophisticated DOS attack in that sense. Smash and grab. So right, so that's a situation where it tries to force or incur a migration and then purposely disrupt it at a very particular point with the intention of trying to get that virtual machine in a bad state so that either the migration doesn't occur and it disrupts the system, or in some cases you can actually even incur a disruption at the very right point and you'll corrupt the original virtual machine image. And so whatever extensions we do to the migration process, it should have that in mind as well. And lastly, perhaps the most insidious type of cyber attack that we're considering is a bait and switch, and that is where during the migration process it incurs a network failure of some kind or some kind of fault on the network, and in the process the migration rolls back and so it doesn't occur, but it's left enough of a footprint on that destination server so that the information on that virtual machine could be exfiltrated. So it leaves the footprint on the destination even though it's not an active. The attacker will still have that information available to them, and operations occur without the knowledge that this type of hack has occurred. So with that said, we'll move on to our actual techniques that we're using in our secure architecture. And many of these have been described throughout the day. So first we'll talk about storage domain and network domain. So our service domains. It's been mentioned on OpenXT Talk and a few others that they employ a technique called disaggregation. What that means is they pull out the drivers from DOM0, which is a monolithic shared resource within the virtualized environment. We pull them up into their own virtual machines. The idea there is if those drivers are somehow compromised, then it's not corrupting the rest of the system. It can't get to DOM0 and it can't get to the other guests within the environment. So if you have your driver, storage drivers and your network drivers disaggregated into their own virtual machines, what happens when that guest migrates? That's a good question. Do you migrate the storage domains with them? Perhaps that's one option. Do you migrate, or do you assume that before you migrate that infrastructure, those storage domains and the network domain, they already exist in the destination server? That's another option as well. And I'll talk a little bit about that in a couple more slides here. Just as a way of introduction, there are a few other mechanisms that also have to be considered when migration occurs in this type of scenario. MAC policies, XSM. There have been a number of XSM references and talks throughout the day. So if you have an XSM policy burned in your kernel on server A and it migrates, you better be sure that your XSM policy on the destination side at least does not interfere with that, because otherwise your virtual machine, your guest virtual machine that has migrated, will not operate correctly. Deletion certainty, that's kind of a simple thing. It kind of addresses that second or that last exploit that I talked about, wherein the footprint is made in the destination side. If an error occurs during the migration process and you do delete that old footprint, or conversely, if the migration occurs and you delete the old footprint in the original source server, you don't want that footprint just sitting around on disk. You want to delete that, fill the disk with either random bits or zero it out. Otherwise, a clever attacker will recognize that that footprint still exists and exfiltrate the data that way. And then finally, I'll give a talk. I'll mention some thoughts on migration policy at the end there, as well as crypto keys. So I mentioned the storage and network, the service domain storage for storage and network. There are kind of two problems specifically with migration. First of all is device pass-through. That device pass-through or PCI pass-through has been talked about quite a bit. With device pass-through, what you're essentially doing is you're linking the PCI address of that device directly to the separate domain. Typically, it's associated with DOM0. With pass-through, it's going to the separate domain, service domain. When migration occurs, if you're migrating that service domain, that pass-through will not work anymore because that PCI address is local to that server. And so when you migrate, obviously it's going to get a new PCI address and it won't work anymore. And in our experience, it's a lot of work. It's actually quite painful to get that device pass-through straightened out after it's been corrupted. Primarily because that storage domain is so tightly associated with that device, it would require a restart of the device, and that kind of violates the whole purpose of migration, or a transparent migration anyway. And then secondly, I have another slide that illustrates this a little better. There's a second path in the service domain infrastructure that's also corrupted during the migration process. This is an illustration of the sort of a condensed version of the ZAPI or infrastructure for storage or Zen server. Other tool stacks will do this slightly differently, but for Zen server anyway, there's a second link there, and it's represented in the upper dashed line. So the PCI pass-through, which I just talked about, is on the bottom there. The second dashed line there represents the association of the physical disk with the virtual back end. That's a data structure that's maintained in DOM0. When migration occurs, that UUID is strictly associated with that physical block device, and so when migration occurs, that link is broken also. And so what is needed then during the migration process is a mechanism that allows you to customize an action before migration and an action after migration to gracefully unwind or undo that PCI pass-through on one end and then reestablish it on the other end. And there's some complicating factors of that as well, which I'll get to in a second. So I briefly mentioned crypto keys, and we haven't done a lot of work with specifically of migrating the keys themselves. There's a lot of literature out there and active academic work in this area, but it is an issue with migration, so I will mention it. The mechanism you use for the actual storage of the keys will dictate what type of migration is needed. For example, the one kind of emerging standard is called KMIP. It's a physical network device. It sits out on your internal network, and it stores. It will securely secure your keys, and it can store thousands and thousands of keys. It's a emerging standard. It hasn't gotten a lot of traction yet because of the price is very prohibitive, but it is an option out there. There's other options for storing your keys, local certificate authorities. You can do it locally, and then there's the TPM itself. And there's a lot of academic work in migrating virtual TPMs across network during a VM process, migration process. But we haven't spent a lot of time on this. Regardless of the technique that you select, it's really the burden of the responsibility to make sure those keys are secure largely falls to the administrator. So just another word on the XSM and the MAC policies. Really, the XSM kind of gets to the heart of sort of the tension between live migration and security. The trend in cloud computing is to make things more accessible, to make it easier to move virtual machines from an arbitrary server, one server to another. With security, you want the opposite. You want things to be static. You don't want things to change. You want to be able to configure them ahead of time and then predictably leave them alone. So XSM is sort of that example. XSM is compiled, burned into the kernel of the hypervisor, and so when migration occurs, how is that XSM policy applied then to the new destination server? And at this point, the easiest route is just to assume that, first of all, you have to write your XSM policies clever enough so that they're not too tied to a specific virtual machine. So that it's a bit of an art form, but you need to establish your MAC policies so that they can be applied across a wide variety of virtual machines. And that's easier said than done. If you have any experience with these XSM policies, they can get quite complicated quite quickly. Secondly, you need to ensure that those MAC policies are identical on each of your server platforms in which migration can take place. And that's the easiest way to do it. Perhaps in the future we can get more clever and provide some analysis in real time. There's a talk in the in the other room just a few minutes ago about making MAC policies more dynamic, and that's certainly a step in the right direction. So in summary, we've brought to bear in our sort of laboratory secure environments that we've established a number of additional extensions to the tools to the tool stack in order to keep migration operating properly in a secure environment. First of all, the pre and post migration scripts, which are not available in all tool stacks. Zappy does support pre and post migration scripts, whereas other more kind of straightforward tool stacks like Excel, you have to build that support yourself. Those scripts get very complicated pretty quickly, and I'll give an example why that is. We saw in a previous chart about how migration operates, all the steps you have. In a secure environment, you have to have contingencies that will roll back the migration in case something happens, in case you have a failure on the server or a network failure. To write that into the pre and post scripts becomes pretty daunting after a while, and some of these scripts are not they're almost written as interrupt handlers. They're not written as to handle multi-threaded operations, which is really what you need, because the scripts need to be able to coordinate with other activities, otherwise their performance is so poor. So putting together the pre and post script migrations properly can be kind of a tricky thing. I mentioned the MAC policy enforcement, which is a very important piece in these types of environments. Group migrations. So in the case I mentioned before, with the case where you're migrating the virtual machine with the service VMs, you may have other reasons for migrating more than one virtual machine at a time. So for example, if you had two virtual machines that talked across a secure internal channel like v4v or another internal interdomain communications, for whatever reason you don't want the communications for the VMs to be across the network. So you make sure you just say by policy that these two virtual machines have to coexist on the same server at all times. So in that case, if you migrate one, you have to migrate both of them. And so that becomes a very complicating factor as well, as you can imagine. So suppose you have migrated one of the virtual machines, and then you're in the process of migrating the second virtual machine, and a fault occurs in the middle of it. What do? Well, you have to, in the correct scenario, you roll back that first virtual machine back to the original server, which may not even be available. So there are, because the network is down or whatever. So it's a very tricky thing to implement. And then finally, something that we've been toying with. We don't have a full implementation of this, but it's an idea that I think will probably gain some more traction here as migration and security issues become more understood, and that is sort of a higher level migration policy. You could argue that perhaps this belongs into the orchestration software instead of the toolstacks, but in any case, it's enforced in the tool stack. So the idea here is that to finding kind of a common language to define how migration rules are set up, and instead of sort of a haphazard mechanism. Some of this is actually available in orchestration software right now, but it's very implementation specific. So the idea is the administrator has the opportunity to explicitly define upfront which virtual machines can be migrated, where they can be migrated to. Alternatively, the policy may be able to define which servers can accept migrated virtual machines, what types of migrated virtual machines perhaps. Really the resolution or the degree of granularity that you want to define in that migration policy can be very specific. But as of yet, there is no really accepted standard on what that migration policy looks like or how it's implemented. And so I think that's something that the community should begin to look at as well. And with that, I can take any questions. You have any? Yeah. Yeah, that's right. Yeah, that's fair. I would characterize it as that XSM, the MAC policies are really at a much lower level, right? They really dictate at the system call level or the hypercall level how the VMs can interact with each other. Whereas this migration policy, which I'm suggesting here, operates at a much higher level. There may be some coordination between the two, but in reality, the migration policy is really almost at orchestration level, whereas XSM is operating at the lower server level. Oh, I see. I see what you're asking. So, right. That capability of within the MAC policy doesn't exist right now. Perhaps there's some extensions down the road that could be had there, but right, the MAC policies at the moment don't have that type of enforcement. Really, they're specific to the server. Those extensions to Mac or just in just a general enforcement? Perhaps not. Perhaps it belongs, at the orchestration level. It'd be easier to implement. That's that I'm okay with that. Mhm. Right. Yeah, and I agree. That would be the most important thing. I think at very least, and we've got this in our lab. At very least, there should be some kind of verification or acknowledgement that the policies are either identical or close enough. And at this point, we're not smart enough to say close enough. Right now, they have to be identical policies before that migration occurs. And if they're not identical, it just won't let the migration happen. Not right now, no. So in ours, which is still really in prototype phase, where this is not production level implementation at this point by any means, we're assuming that the infrastructure is identical. So the service domains are duplicated on both the source and the destination, so that when that VM is migrated, it essentially reestablishes the plumbing, the PCI pass-through, and all the service domain, as well as the XSM policies and the labeling and all that. That assumes that infrastructure is in place and it doesn't have to recreate that. That's a harder problem that we haven't tackled yet. In theory, they could be, yeah. And perhaps, I don't know, can't think of a scenario that would justify that offhand, but perhaps, yeah, or there's for whatever reason you've got a dedicated virtual machine on there that needs some special policy, whereas these other servers don't need it. And in that case, to maintain that cloud environment, you still want to be able to support migration. It's a little far out, but maybe it's viable. I don't know. Right. Okay. Well, thanks for sticking through this, New Hampshire.